Hello everyone. So today we will start talking about some teeny improvement of modified matrix encoding. So the idea behind of that kind of improvement is that the general steganographic method as the matrix encoding has been improved by placing that word modified. So, and we already discussed that particular method. So remember, the modified matrix encoding means that in each block, so we are going to modify a few coefficients instead of one by hiding the same amount of data. So, and such kind of modification can give us some improvement. And again, we already discussed how big is that improvement. Now, what else we can change in that particular scheme? So technically, the general procedure of modified matrix encoding, or MME, is presented here. So we are using some test JPEG image. So from that JPEG image, we will extract non-zero DCT coefficients, and those DCT coefficients are presented here. So this 1/n, where the n will be the number of non-zero DCT coefficients taken from the JPEG image. So based on the general procedure, I'm supposed to divide my image into the set of blocks. So we will need to calculate like how many what will be the scheme, matrix encoding scheme, to hide necessary number of bits inside of that particular image. And at the final moment, we will also calculate the matrix encoding block, which is the 2 power n minus 1, where the n is the number of bits what we're supposed to hide via each block. Okay, and after that, we will start hiding our data into the image block by block, until the block K. So remember that particular number, 2 power n minus 1, the block size is predefined by n, and we cannot simply choose the block size of the random length. So the block size is fixed, and the difference in between one scheme to another scheme will be pretty much significant, and we will have to handle that kind of situation. That's why we can easily meet the case what is displayed here. So based on the data what I want to hide, based on the n, what the number of non-zero coefficients, so we decide that that's supposed to be this n. So if I will get bigger n, so the biggest, that small n, so the bigger number of bits per block, the capital N, which is our number of coefficients, will not be enough, and I will not have enough coefficients to hide my data. That's why I need to go for a smaller n, and that will give me enough room for hiding. But what does it mean? It means that this part of my DCT coefficients will not be used. In general, that does not change much, because as long as I can hide, yeah, this is the way to go. But there is always the way to improve that particular scheme. And today we are going to discuss like how to, without modifying the general method, to hide same amount of data, but at the same time, the efficiency of the data hiding will be higher. So without doing the general improvement. So what exactly we need to do? So here we are coming to the improved modified matrix encoding, IMME. So what is the idea of that kind of improvement? So the first part, where the block, our image will be divided into the K block, will keep same. But here, instead of using the K block, what we had in the previous scheme, so here we will use the K1 number of blocks. So that K1 is definitely smaller than K. So, and the rest of the pixels here, so we will use to create another matrix encoding scheme with the n plus 1. So the blocks for the second scheme, so they are bigger, as we can see here. So, and the difference can be very much significant. Okay, and now what we need to do is to balance K1 and K2 such that we can hide data in using the scheme 1, using the scheme 2, and that particular part, what is in the middle, will become as small as possible. See, in the original matrix, like modified matrix encoding scheme, that non-used part is pretty big. Sometimes that can be like up to the 50% from the image coefficients. Mostly depends on the amount of data you want to hide and the number of available coefficients. Okay, but using those two schemes, we can minimize that particular area into the few hundred coefficients, sometimes even less. Like it depends how can we balance K1 and K2. Okay, so this is an idea. We will not modify the matrix encoding scheme. So we will not modify the way how to hide data into the image. So what we will do is to insert data into the image using the two schemes simultaneously. And that will maximize the number of coefficients what we can use for hiding and minimize that number of non-used coefficients. And as default, we can significantly increase performance of data hiding. And at the end, so we will see what is that particular improvement. Okay, now let's start coding. So this is our general framework. So come to our source code. So this is our previous code, modified matrix encoding version 1, encoder. Okay, so let's go to the 5 here. Okay, I will call it improved MME encoder. So image is the same. Okay, so Stega. So let's modify the Stego image. So okay, that part I will not touch. Okay. So we also need tools. Okay, just to make sure. So we can run it without the problem. Okay, so get pairs. So we use the get pairs function, it's not exist. Let's save it. Okay, so it works. So finally we can see the image. So here is our image, what we're supposed to get. Definitely now this is not improved, but anyway, at least we know that there is no any issues related with the coding and like folder connections what we are using here by connecting the JPEG toolbox to that particular source. Okay, so what we are going to do next? The first of all, we will need to get our coefficients. So Okay. So let's stop here. So get proper n. So that n is for sure the n what we will have to use. So that will be that n what we design. So the problem is that those portion of the coefficient can be pretty big. So and we will need to minimize it. So okay, so the first what we will need to do here is to compute balance or find the optimal numbers of blocks for n and n plus 1. So see, up to now the number of blocks what we calculated here will not be that number anymore. So we will need to calculate. So here that should be like n blocks 1. So in order to get those proper numbers, so the number of block 1, so technically I don't know. And so here this is nothing else as our K1. So this one, like I don't know yet how to calculate it. So that will be the K1, and also I need to get K2. Okay, and both we need to find. So what exactly we can do here? So there are two equations what we will need to remember. So remember here, okay, so here first of all that will not be exactly equal, so but we will need to get the number very close to that, like to n. So that's why let's consider that I will have to get K1, K2 such that this equation equal n. So for sure, like K1, K2, we cannot get exactly. Why? Because those two numbers must be the integer numbers. So we need to do something that's called the integer optimization. But we don't have it right here. So, but anyway, we can handle. So, and the next equation related to the message size. So, n, remember the n, this is the number of bits what I can hide using the first scheme, n bits. K1 is the number of blocks. So the message what I will say of what I will hide using the scheme 1 will be the n multiply K1. So for the second scheme, n plus 1 multiply K2. So here that will be the number of bits using the second scheme. K2 will be the number of blocks for the second scheme. And those two numbers must be the same as the message. So if we can find the K1 and K2 such that we can keep both of them hold, so that will automatically solve our equation. So, and now we need to figure out how to do it in Matlab, because definitely here must be the way how to get those two numbers. So how to process that calculation? So first of all, we will need to make a matrix. See, here there are two equations what we will need to solve simultaneously. And let's try this. Okay, so matrix M. So the matrix M is our numbers, like our coefficients, technically, for the linear system of linear equations, 255 and 511. So that will be our two schemes in terms of the K1 and K2. So here there is no K1, K2. So, and matrix R. So the matrix R, this is our right side, will be the N and the message size. So R, this is like 413,000. Message size is 10,824. Okay, so now how can I get K1, K2? So in Matlab we can process like special division is actually accelerate specific numerical method how to get the answers, and so by using that equation we can get the answer 1011 and 303. So definitely those coefficients, so actually the first number, this is our K1, the second number is our K2. So if we will use them directly, we can get N and M. But remember the K1, K2, this is number of blocks. So then number cannot be float. That should be integer. So integer number. And now, like what exactly we can do here in order to resolve our problem. So technically, this is our first approximation. What will be our coefficients for hiding? So now, how can I check? So now I will need to combine those two equations and check whenever it is works or not. Okay, so let's make K1 equal X in the position 1. Okay, and let's do seal first, because I don't know how exactly it will work. So this is the 1012. Okay, and K2, so that will be our second. 204. Okay, now let's check like K1 multiply 255 plus K2 multiply 511. KR. Yeah, see the problem. So now the number of coefficients what we need using that particular scheme is bigger than we have here. So in our case, that number must be smaller. So actually, see the problem here, if we will make the scheme 2 bigger and scheme 1 smaller, so the number of necessary coefficients like will remain smaller. So in order to fulfill our conditions, so technically what do we need to do is to reduce K2 and increase K1. So and finally that like we can balance our numbers. Oh, by the way, let's try for the message. Okay, so here if I will place 8 instead of, so here 9, so that will be our second equation. Okay, and see here I can hide more bits. So it means that our capacity in theory now is bigger than the message what I have. So, but at the same time, see, we need more coefficients for that. So that's why it gives us the way like how to balance it. So as I said, so if I will make that K2 smaller and K1 bigger, so I will reduce so the theoretical capacity. At the same time, I will reduce the number of necessary coefficients. Okay, so now if K2, so 304, I will make 303, and K1 I will make 1013. Okay, now I'll come back to that equation. Okay, still doesn't match. I think instead of sail, better to do floor. Okay, so let's do this. Instead of sail, let's use floor. For K2, explore. Okay, now this equation R. Okay, see now that number is smaller than this number. 1011, 303. Okay, and this number. And this number is smaller. So now we do have an opposite problem. So, and if we do have an opposite problem, so now what we need to do is to increase the numbers. So, and move our like situation back. So, and see whenever our coefficients, they are correct or not. Okay, so I can now decrease the K1. So, and actually we can calculate the difference. Okay, let's calculate the difference. So this number minus this number. Oh, 477. So see, this number is smaller. So this is our block size, 255 and 511. So this number is definitely smaller than 511. Otherwise, the balancing part will be different. But that number is still less than 255. Means that I can easily add 1 into the K1, and that will not change much in my equation. So the number will be still okay. So if K1 I can increase to 1012 and come back to our equation. So we can see this number is still suitable. Stop. 12. Okay, minus 3. So, and if I will subtract. Yeah, see, 222. So now this number is smaller than 255. So it means it is still possible. Okay, and the next what we need to check is this equation. 23. Oh, okay. But we need 24. So, and what exactly can I do now? So the K1, I can increase by 1. But K2, I can decrease by 1. Mm. Okay, I think the best what we can do here, make some simple check procedure and just ask computer to calculate the K1, K2 like as they supposed to be. Okay, so here okay, let's make a while loop. True. So and here let's check. So if so, this condition is bigger or equal C. C here is our message, and this condition must be smaller or equal n. So if so, run false. Okay, and here we will need to do some stuff. So again, so the first what we can try is to increase our k. K1, 1 plus 1. Okay. Okay, so in here we can check. So because if I will increase that continuously without any like check procedure, so here I can mention that. So if in some moment that particular number will become bigger than n, because definitely that will, because we are increasing k1 and doesn't change k2. So here let's change k2 as the k2 minus 1. Okay, and here let's check k1, k2. So this number and that number. And let's see what will happen. K1, K1, floor x1. Two, 0, 30, yeah, okay. So and finally we can get the number. So the message is 10,830, and this is our necessary number of coefficients. And if we will check, so that number is smaller than the number of necessary coefficients, and you can see the difference will be very small. Let's calculate what will be the number of non-used coefficients. (223) coefficients. So if we will come back here, so this is that is our area. Just 223 coefficients will not be used. So and we got like k1 and k2, and those numbers we will use later to process our coding. Okay, so the next what we will need to do is technically modifying the code what we already have here. See, the problem is that I will have two schemes, scheme 1 and scheme 2, and now everything must be double in our application. First of all, even that H matrix, so here, so we will need to change like block size. Oh, block size. Yeah, I think I deleted. So the block size, let's call it like scheme 1. So that will be the 2 power n minus 1. At the same time, I will have block size scheme 2. So in here, instead, I will have m plus 1. So, and here, for the h2, so here I supposed to use block size scheme 2. So this part. So now that again will become different. So here, similar, I will need to divide that coefficients. See, y and z, this is my non-zero coefficient. So starting from the first one, so here I supposed to get the number of blocks. So that will be for the scheme 1. So here n equal 8. So the number of blocks for the first scheme is this number. This is our K1. So that's why instead of number of block, I will use the K1. So here, so that should be like size block scheme 1. Okay, so what will be the second block for the scheme 2? As long as this number of coefficient I already occupied, so I cannot start from 1. I should start from that number plus 1. So, and here I supposed to place my coefficients, like that will be, so this number plus second scheme, so here 2, 2. So for sure, like we can start from the end, yeah, but logically wise, this is better to like take first few coefficients, process the scheme 1, after that take next coefficients from the scheme 2 and just combine them together. So that's what will happen here. So the second scheme will just go next to the first scheme, and our non-used coefficients will not be in the middle, they will be at the end. So, and that will be our scheme 2 for n equal 9. Okay, same I will need to use for use CH1. So this is our coefficients. It's better to just edit here. Cool. So, and because the coefficients will be the same, the number of coefficients, so that's why I can just simply do this. Так, original LSB, same, that should be CH1. CH1, this is CH2. So that is our original LSB, size is same. So this is great. Okay, so now reshaped CH1, CH1. So here the size block, this is the K1. Block size CH1, number of blocks K1. Let's do it for the second scheme. So here second scheme, second scheme, second scheme. So this is the same. So here K1, and that is our H1. So here 2, 2, 2. So and same for the original LSB. H1, ch2. ch2. Okay, size block ch1, ch2. So here k1, k2. Okay, now data. Data is interesting. So because the data we divide into the two parts. So now let's divide the data again. So, but with the data, the problem is that, okay, so see, the number of bits, what I can hide is 10,830. But our message is 10,824. So means that the 6 bits I will need to like pad. So we will need to make our message bigger and meet the capacity, the message, like the available capacity from the method to the message what we want to hide. Now that message is smaller, but we can always add some parity bits, some extra information, like and make the length of our messages same. So that is something what we can always do. And for the same reason, I will need to like divide my like data row into the two parts. Okay, so that's why once so add padding bits to message. Okay, so we can calculate the capacity as where is that? K1 and so here will be the n multiply k1 plus n plus 1 multiply k2. So that is our total capacity. So this number is 10,830. Okay, now pad. So that will be, I see. So that is capacity minus C. So C must be our message size, 10,824. So, and now I will need to modify my data row. Data row, let's call it pad. So that will be the data row plus, and here let's add either 1 or 0. Let's add zeros, 1, pad. So then if I will stop here, okay. CH1, use CH2. Okay, so and now we can see the number of bits to hide is exactly the same as the capacity of our method. So capacity is same number. Okay, and now we can divide our message because, okay, see, if I want to reshape, so I supposed to divide my data into the two parts as well. Let's do it here. Divide message two parts. Part 1, H1, scheme 1. Everything is the scheme 1. So that will be our raw data. But how can I get it from 1 until? So I know the number of blocks. This is the K1. And this is the 8, the number of bits per block. And that will be our scheme 1. So now the scheme 2, like the data what I will hide into the scheme 2, that will be so like starting from the next bit, and here that will be n multiply k1 plus n plus 1 multiply k2. So and finally we will spread our data into the two schemes, scheme 1 and scheme 2. Okay, and for the reshape, I again need to do this kind of schematic. Like, so take this data and process it. And this is the number of bits per block. And here I'm supposed to place K1. So this is the number of blocks in the scheme 1. So here, 2, 2. So here will be n plus 1, K2. So pairs. So the pairs we need, as long as we will use our modified matrix encoding. So I want to keep using that modified version of our method. So and I will just need to process our schemes like in a different order. So the first I will need to use the scheme number 1. Next is the scheme number 2. Okay, so here. So that will be the scheme 1. So let's see what is this. This is n equal 8. Yeah, our like block size ch1 is 255. Okay, and everything we already have. The original use rs. So we already spread them, like split them into the two parts, like ch1. Okay, so here number of blocks. This is again number of blocks for the scheme 1. Number of blocks for the scheme 1 is k1. So that's why here will be the k1. So rh ch1. Okay, message I will get from here. Okay, calculation of the original message, syndrome, position, Q block. Okay, so the Q block we will also need to get. So that Q block is coming from the Q use rs, but we have the Q use rs scheme 1. So that will be for the scheme 1. Okay, so that part we can like skip. And for the modified coefficients. So here we are modifying our y use rs. So as long as we do have, again, have 2 of them. So I will use the scheme 1 here. Scheme 1, scheme 1, scheme 1, scheme 1. So and here a 2-flip solution as well. I will just change it to the necessary scheme 1. Okay. Okay, so and now everything same I will need to do for the scheme 2. Exactly the same. Just I will need to handle the different numbers in a little bit different order. So that's all. So let's do the same for the scheme 2. I will just copy this part, place it here. So this is our scheme 2 and 9 blocks times scheme 2 to 511. So here will be the K2. We will get original LSB from scheme 2, like RS, that's why we divided. Message will be taken from again S2, like scheme 2, like syndrome, Q block. So here 2 as well. Okay, pairs, Q block, distortion. Okay, and after that I again need to modify all of our coefficients, what I'm going to change from scheme 1 into the scheme 2. Okay, so done. So and if I will stop here, so technically that will means that our data hiding path into the blocks finish. Data row, that should be bad. Okay, that's part I also missed. See here I supposed to use H1. Remember, we do have two schemes for the H1 and H2 for the scheme 1 and scheme 2. Block size H1, block size scheme 2, CH1, CH2. So and here that should be H1. Here that should be H2. Okay, here H2. Run. Okay. This part also must be changed. And here. Okay, and that messages we don't need. This is for the verification. Aha, okay. So here for the, see this N is not same anymore. So we are using like N plus 1. So here should be N. Okay, so in case of pairs, this is also important. See, when we call the pair, so here I insert N. Okay, I can keep those pairs untouched, but for the scheme 2, so here I need another pairs. So definitely for different schemes, so those pairs calculation will be different. So here I need to place like N plus 1. So here will be the pairs like for the scheme 2. So now everywhere we are using the pairs, I need to change. Okay, and let's change them here as well. CH1, even if it works, better to place correct version. Okay, position, yeah. Okay, let's try. Okay, done. So looks, we already hide data. So now the problem is like how to get our image back, because even in the modified matrix encoding, like in the code what we had here, so now that will be the case. Like how do I have to handle my coefficients in order to get my image back correctly? Well, first of all, like this y use rs, it doesn't exist anymore, because we do have like scheme1 and like rs-ch1 and rs-ch2. So, and that will be slightly different. Okay, so what I can do, like ch1, ch1. Okay, so here size block ch1, and instead of n of block, so here will be the k1. So, and I can do the same for like for the second scheme, and after that, like my y mod, so that will be nothing else as the unification of scheme 1 and scheme 2. Okay, so here, so see y and z mod, that will be our non-zero coefficients. So now the necessary part of them I will need to change. So before that was that particular part. So, but now that will be this part, and only that part will not be touched. So that's why here, technically, I can do this. This is the number of bits for the scheme 1. This is the number of bits for the scheme 2. Okay, and rest will be the same. Okay, let's try. Okay, done. So now we create our image. So that image must contain hello students like image inside. So, and similar to what we did before, now we need a decoder. So compared to the matrix encoder, modified matrix encoder, what we discussed last time, definitely improved version will need a modification, because as long as we do have like two schemes, so that will definitely affect our code for the decoder. Okay, so that's why let's get this file. So that will be our improved MME version 1 decoder. So here, what was the image? Still improved MME version 1. So that will be our image. Okay, that part will become same with again some modification. Okay, so res reshape, can get zero coefficients. So now decoder message size is fine. Blocks message size divided by n1. Okay, so technically I can process the calculation like based on the message size. I can process the calculation of the K1, K2, same as what I did in the decoder or in the encoder. Okay, so here I can compute K1 and K2 similar to encoder. Why again? Because I know the message size. So the message size was our original information. So technically, I can skip that calculation and just add K1, K2 into the side information. So, but in reality, so we will send only the information what we cannot calculate. So that's why better to process that calculation. So what we did here. So and that part will give us like K1, K2. Let's check. Okay, I don't know N. I don't know N. So at the time when I calculate the number of non-zero coefficients, I can calculate N. Okay, so the message size, this is my C. Okay. And Z mod. Yeah, because the number of coefficients, yeah, 14, 302. So that is that K1, K2, what I had in the encoder. So we can check, is it same or not? And see, the number is same. Yeah, that should be same because we didn't modify the number of non-zero coefficients. Okay. So we got like K1, K2. So again, so here the number of blocks. So that will be the CH1. Okay, the number of blocks, in our case, this is the K1 and K2. So technically, we don't really need it. So the block size, yeah, so that we will need CH1. And I do have a block size for the scheme 2. So here will be the M+1. So similar to the previous case, so here will be the 2H. I can just copy from here. H1, H2. Okay, so record it. Okay, so that particular coefficients, see, this is the coefficients what I need to get my LSB and process. So here again, I will have two of them. So record it for the scheme 1. So, and for that, I will need to process like a number of blocks. That is K1. Block size. This is the block size scheme 1. So if I want to get that for the scheme 2, so I supposed to start from here, and here will be the like the number of coefficients in the scheme 1 and in the scheme 2. So, and for the modified LSB, again, here I will have the scheme 1. and for the scheme 2 as well in the similar manner. Here will be 2, 2, 2, 2, 2, and 2. So this shape is again the same as long as I do have two schemes. So here will be the blocks like size of the block ch1, so number of the blocks k1. So for the scheme 2, so here should be 1. Okay, here 2. Okay, so hidden message rs ch1. ch1. Okay, so here n k1. So for the scheme 2, so that will be the n plus 1 k2. So now, and again, like decoding, I will have to process in the two step. The first for the scheme 1, n equal 8. So start from 1 until k1, res ch1, ch1, h1 is mod 2. Okay, and the same I will need to do for the scheme 2. Yeah, 9. The number of blocks for the second scheme is the k2. Here should be 2. Hidden rs 2 and h also 2. Okay, and after that, like recover our message like ch1. Here will be the rs ch1 like n number of blocks k1. For the scheme 2, here will be 2. Instead of n will be the n plus 1 because this is our second scheme, and k2. K2 is the number of blocks in the second scheme. Okay, and now in order to get our hidden message, so I supposed to combine two messages. Hidden like message ch1 and hidden message ch2. Okay, so here there is another problem. Remember the message size now is 10,830, but real image is 10,824. So in the beginning, before I hide data, I supposed to add padding bits. So here, before I will display my image here, I supposed to delete those particular padding bits. Okay, so in our case, we already know the size of our image. So this is our message size. We already calculated. Okay, so here I can just write like message size plus 1 until end equal nothing. Okay, so here delete padding bits. Okay, so and after that, so my message should be good enough in order to be displayed in the screen. Okay, now let's try. So if everything is going well, yeah, I can see the hello students. that's what is happening. So now we modified the second, like the decoder for the improved modified matrix encoding. So and finally we got our hidden message. Okay, so that's all for today. So you can practice with designing the encoder and decoder for the improved matrix, modified matrix encoding. So and that will be the good enough, like to try something which is really useful. Remember, like the first two improvements what we already made for the matrix encoding, that was great, but that improvement what is happening right now, this is really final. So in reality, like in real situation, we definitely can use that particular technique. So because we already improved it twice. So definitely later we can improve it like even more significant. But that will be our next topic. Okay, that's all for today. Good luck.